chemistry, which was held in Villa Planetarium. The second lecture was in medicine, that was in ACL, National Library. The third one was here. So this is the fifth successive year we are having all the three Nobel. We continue to do that. So it is being organized by Tamil Nadu Science Forum and as you know, Tamil Nadu Science Forum was founded in 1980 by few researchers in Madras University who are doing research in this department. One of them is Professor Rohit, he is here, he was the founder member. So we have organized a lot of lectures in the 80s. Later, we think that instead of having the lecture in hall, let us go to the people. So we started a journey and go to the street and demonstrate something. And again, it ended up with a big march of science march from Kanyakumari to Chennai. So that was an interesting history. After that, when we get into the literacy movement. The literacy movement, we get into Virudhunagar district and later Pudukkottai district, and we get a lot of volunteers, and the organization is find that. Now it is working on the six different verticals. So one is the science propagation we are doing. The other one is the science propagation. We are publishing a couple of magazines, one in Tamil, the other one in English. Apart from that, we also publish the science books in Tamil. The Tamil magazine is Tulip, which was started in 1987. It is the only magazine which doesn't have any, we don't have any advertisement, and it is having a circulation of 430%. The same way English Jantar Method is for the students of college level students. And we also have published a lot of science books in Tamil. Apart from that, we have another wing that's working on women in science, that's called Samam. And another science for youth, another wing working on science for youth. We have another vertical which is working for development and environment and development. So there are 6 verticals working under that. Any of you interested in any of those things, you can join and you can get involved in science. And PSL is 160. So that is coming under the science propagation. With that introduction, so we will have a lecture on the Sivarama Krishnan come and thank you for accepting it. I extend my warm welcome to you. He is giving a second lecture. No? Again, whenever the optics won the Nobel Prize, he will be our speaker. The last time he spoke about in 2019, but then after 4 years we started. It was Dr. Professor Rama, Pierre will be introducing the speaker. After that,
thank you very much. I will not take much time. Number one, he needs no introduction, but I need more introduction. Second thing is, whenever I have doubts and questions on optics, particularly quantum nature of optics, I immediately look for him to answer the questions. And I bother him with several questions. Even now I am doing what he has. Okay. So hopefully some of them will be interesting. Dr. Sivarama Krishnan, for others, he did his Ph.D. from Max Planck in Heidelberg, nuclear sciences, right? Nuclear. And then moved to, for postdoctoral thing, he was there in IIT Madras. Then he joined here, right? Yes. In IIT Madras. When did he go? 2014. Okay, about 10 years back. About 10 years back, he joined, and he is extremely helpful. Whenever I ask him, particularly about science lectures, he immediately accepts. He did give a talk on optics and again process. One of the things, the time scale which he was talking about at that time, is femtosecond. Well, you can say it is 10 power minus 15. Yes. 10 power minus 15 seconds. So you are thinking about very, very, very tiny scales of time. Just like that. This itself is quite large compared to that. And that is the kind of time scales you are measuring. And you want to have see what happens in molecular interactions, chemistry, etc., etc. And if I remember, he was also mentioning about people are trying to push the scale even at that time. And he just now said within 5 years they have actually pushed it. And now we are talking about attoseconds, and for mine 18 seconds. It's so tiny. It's still tiny, this thing. So you can see the extraordinary things that can be talked about in those time scales, where limits of quantum limits are going to be seen even in experiments. So I will not bother you more with the marks. I will request Dr. Sivarama Krishnan to proceed. Thank you.
Afternoon, everybody. It's indeed my great privilege and pleasure to be here once again. As Professor T.R.G. said, in about 5 years' time, to once again do the honors in talking about the science of the current year's Nobel Prize in Physics. But before I proceed to any of that, it's actually a remarkable thing that this forum is doing within the state, beginning with Professor T.R.G., Mr. Vijayan, Mr. Sundar, and all the colleagues here, in the sense that science is a very human endeavor. It's done by people. It's in some sense received by people in various forms, including technology. But then, while we are more often than not beneficiaries of this, we seldom maybe have time to pause, look back, and think about how it is done, what is done, and so on. In that sense, the TNSF is locally making waves, just like we're going to discuss about in this talk in terms of making light waves. They're making science waves in this society. And the state of any society is, of course, measured in terms of a lot of parameters, economics and maybe even happiness, like whatever else that one can think of. But very often, it's the level of science and technology that the society is aware of, maintains, and grooms its young minds into taking up is what makes a big difference, makes transformations, makes even huge revolutions. In that sense, the contributions of this forum and fora like this are quite immense, especially in a country like ours where we speak at least 40 plus main languages, even a much larger variety. To take science to the different corners of this wonderful country is a very challenging task. And in that, as we just heard, this forum makes a remarkable effort and has considerable success in attracting audiences, specifically very young minds in the form of students across various disciplines. So with that, I should actually thank this Tamil Nadu Science Forum colleagues, again, Professor Govindarajan, Professor Vijayan, Mr. Sundar, and colleagues, for keeping me in mind and giving me this opportunity to bring home the science and the story behind this year's Nobel Prize. It may actually have been very appropriate that I did this in the local language and my mother tongue Tamil. However, when it comes to technical speaking and thinking, perhaps that's something for people like us to think about. We still prefer to do it in an international language. So my apologies for that, because once I brought this up to some colleagues, they asked me, "Are you going to give this lecture in Tamil?" I said, "I wish. I wish I had the guts to." Both of which I hopefully will make up for in time to come.
You can practice.
I can practice indeed, and I can get some help too. So welcome once again, everyone, to this evening's what I would call a technique with ultra fast science. I will go through my lecture as I've prepared it. However, maybe at some intermediate junctures, if I go too fast or if I'm going too much overhead, please don't hesitate to interrupt me and pose your questions. There's audience live here as well as online. So in both media, this is very welcome. And let's start this journey. So what we see here on the screen is, as Professor Govindarajan observed, so many zeros. Just one, a little one. So a billionth of a second is an attosecond, right? Come. Billionth of a second is an attosecond. We can barely even imagine it or feel it. That is really the challenge, right? So today let us talk about conceiving and the developing attosecond pulses, which led to this year's Nobel Prize. And I like to subtitle this as there is plenty of time at the bottom. Physics students are perhaps very aware of this landmark statement made by one of the greatest physics teachers and physicists of all time, which is Feynman. He said, there is plenty of room at the bottom. So when we do things like this, or mankind does things like this, we probably should start to realize that there is plenty of time as well at the bottom. Once again, I'm also grateful to my institution, IIT Madras, for facilitating some of the science that we do along this direction. If you are curious about this, or questions, comments, any other inputs following this talk, please feel free to drop me an email at any time. And if you are even more keen, you can also join us in this adventure which we take up in our laboratories. So an outline, or at least the way in which I envision presenting this talk here, is to, of course, talk about what is an attosecond and why exactly should we be concerned about it? Why should be so big that realizing such pulses gets people to the Nobel Prize? How do we generate and measure these attosecond pulses? What made it possible? What was the road to this milestone? And as I said, science is a very human endeavor. So who paved this road? Who all? It may not be an exhaustive list, but at least the stories that I'm aware of. And then the important question, what have we done with it in terms of science, physics, and what can we do with it in terms of science and technology? Right? And finally, and hopefully, I'll be able to convince you that the ultrafast world is so fascinating that I hope this talk serves as an invitation to this aspect of the universe for many young minds who are listening to this now or perhaps later. So let us jump straight into the prize itself and take a peek at the most important statement that the Nobel Committee gives along with the felicitation for the three laureates. The three laureates are Anne Louis, a French, native French physicist, but who did and does all her work in Sweden, in Lund University. Then Professor Ferenc Krausz, who is at the Max Planck Institute for Quantum Optics in Munich, Garching, Munich. And Professor Pierre Agostini, who was for a long time at, I think, at Texas, University of Texas, but now he is back to his home country in France. The citation reads that they received the prize for experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter. So, a couple of important things to know. Generation of attosecond pulses, that is an important aspect. It's a science of making, but making also means measuring. And primarily, this is employed to study the dynamics of electrons in matter. Now, as Professor Govindarajan alluded to, and as I'm also trying to get you to think about it. And an attosecond is something which we typically cannot even conceive in our minds as easily unless we probably have some analogy or reference point, because most of the motion, the time scales, and things that we come across around us are in the millisecond time domain, right? So if you take the fastest human being who runs, we say, okay, he ran 100 meters in 9.85 seconds, that is 9 seconds and 85 milliseconds. So you compare that to the national record of, say, of 100 meters in this country, maybe 3 seconds or something. It's only 500 milliseconds apart. But then if we look at our own clocks, our clocks tick second scale, but then there is something millisecond going on, right? So all this gives us a feel for the millisecond bullet, which is the way we perceive nature with our five senses around us. But to put this new adjective, atto, in perspective, we can examine the extreme scales of the universe, perhaps, right? Compared to a reference point, which is us, you, me, and everybody, the heartbeat. Our heart beats roughly at about 1 beat per second, a little faster or slower, depending on our state of health and so on. But then if I write down the age of the universe in seconds, what's the age of the universe? Can somebody shout this out in years? What is the age of the universe in years?
13 billion.
13 billion years. Billion with a B, as Carl Sagan would say. It's 10 to the 9, 10 to the 10 years. And in terms of seconds, it is of the order of 10 to the 18 seconds. It's a billion times a billion, right? So the ratio or one heartbeat in comparison to the age of the universe is what an attosecond is to the period of a heartbeat. It's as tiny as that, right? And we of course live an average human life at best can be at, say, of the order of 100 years. So these dimensions are possibly not something we think about daily and can conceive it, but I hope with this sort of an analogy, we start to feel that these are extreme time scales, extreme scales of space and time, right? In fact, the physics of this very large time scale and physics operating on very small time scale has many similarities, but also can appear to be considerably different. Okay, so that's a psychological feel for what is an attosecond. But then this is physics, not psychology. So let us try and get another feel or a numerical feel for what an attosecond is. And this is basically a simple calculation, assuming this is a class for a very curious audience, which all of us can do. So I see some people even having their pens and papers and notebook out. So that's wonderful. So please join me in doing this, right? We all know about the hydrogen atom. The iconic hydrogen atom, the simplest element in the universe. The nucleus of the hydrogen atom contains a proton, and we are told, at least at some initial level, that look, there is an electron that orbits the hydrogen atom, which is not technically very accurate, but we will come to that in a moment. But then, in the spirit of planetary science, if we were to assign a radius for this orbiting electron, that radius is about 0.1 nanometers or 1 angstrom, as it is called. So let us take the circumference of this, the path that the electron goes around the nucleus to be. This is approximately 3 times 10 to the minus 10 meters, right? This is good. So inaccurate picture, but we can imagine the electron to be a planet moving around the protonic sun or the nucleus of the atom. By the way, the nucleus of the atom is 1 femtometer or 10 to the minus 15 meters. It's much tinier. The length scales are far different from what we have for the Earth-Sun system in terms of planets, right? What is the velocity with which this orbiting happens, right? Again, I must warn you that this is not the right physics picture, but it's a useful one to drive home a point. The velocity, if you wish, is about 100th the speed of light. It is physics trivia. You take the speed of light divided by a very famous number, 137. Even in physics, there are such numbers, but that number does not even have units. So it's really a remarkable number. Multiply this one, you get the velocity of the electron in this hydrogen atom. So this is the speed with which it goes around at any instant of time. So now if you have your pens, papers, and a calculator in your mobile phone, please take it out and tell me what is the time the electron takes to go around once and finish one revolution around the nucleus. And we quickly compute this number. Maybe you don't even need pens and paper. Really smart people.
10 power minus 16.
10 power minus 16. Yes, Professor Piaggi says 10 power minus 16. You can your answers can be different, could even be better. 1.5 to 10 power minus 16. 1.5 to 10 power minus 16. Anyone else? Okay. That's right. It is 1.5 times 10 power minus 16. It is 150 attoseconds. Right? So it's 100 attoseconds approximately. So now this is the simplest piece of electron dynamics we can take, right? To reconstruct a planetary system with an electron and proton, all other characteristics being the same. If the hydrogen atom were for any reason classical, which cannot be, then this is how the orbital's period would have been 150 attoseconds. So if we were to really get a feel for why attosecond physics or why attosecond pulses are important, if the electron were to be revolving around the nucleus like this, and we were to take a snapshot of the electron's motion, then to take a snapshot of a dancer dancing with motion of the order of milliseconds to a second, you need a camera flash which is one. Say your cell phone camera, or the DSLR camera, they have flashes. These are all operating for time scales of a micro or of some microseconds. That's why we call it a flash. A camera that can flash and take a picture or a snapshot of one position of the motion of this electron would have to be therefore of the order of attoseconds, which makes us the point that if you have such tiny light flashes, you can study electron dynamics. Right? This is exactly what the Nobel citation told us. But then that's the problem. How do we make these flashes come out? Flashes of light come out. Right? This is one immediate challenge, but this is a very classical picture, right? And I'm sure my physics colleagues will say, don't miseducate these or misinform these young minds to think that the electron goes around like this in a circle around the atom. That's actually not true, right? Do electrons orbit? Electrons have no orbits. That's what quantum tells us. There are no trajectories. It's a very different universe. So then how do we reconcile electron dynamics and attoseconds? So Uncle Einstein says think and think carefully. Right? So let's think carefully about this. And for this, to take up Einstein's think carefully, I would encourage you to, if you know a bit of quantum mechanics, great. This is something we would have studied in our first quantum mechanics course. If you haven't studied any quantum mechanics, or you're here as a curious mind, without physics being one of your main subjects of education, but something else, then even then we can get a feel for what's happening inside the atom, if from a quantum mechanical sense, if you don't really get intimidated or bothered by the math, right? So come along and see what happens. In a hydrogen atom, the same hydrogen atom with the proton and the electron, the math looks like this. For those who are familiar, this is obvious. Whereas, what exactly is happening here? The proton and the electron are interacting with a Coulombic force, and this is something we learned in high school, that the force of attraction or repulsion between two charges, unlike or like respectively, essentially is an inverse squared law. The force diminishes as 1 over the square of the separation of the. So we write down the potential between these two, between the electron and proton, right? So what is the potential? We can roughly say this is the voltage electron and proton. So the electrostatic force, the electric force that holds them together, has this voltage as a function of time, and it scales as 1 over the distance or the separation distance between the two. And in the numerator, you can see the square of the charge, right? So this is actually all we need to know. And there is a prescription of Schrodinger's quantum mechanics, based on which we can figure out the entire life history of an element. That's the whole idea, right? So, but then this is not a physics quantum mechanics course. So let's take inspiration from one of his physics, one of the most brilliant physicists of all time, Paul Dirac. He said that I consider that I understand something in physics when I can predict something without actually solving the problem. So let's try to predict, right? Almost like who's going to win the 2023 cricket World Cup. We have some really good predictions, right? The way certain teams are playing, and maybe we favor the color blue and so on. So let's predict stuff about this equation without actually solving it. What can we predict about this? Now, if a physics student looks at this equation, he or she would say, look, H stands for Planck's constant. It's a universal constant. Okay, it's like a currency for a certain physical quantity. M here is the mass of the electron. It's again one of nature's fixed points. The mass of the electron is a very important number. E is the charge of the electron. So this entire equation has other symbols. The very famous psi, which looks like sometimes looks like the Indian Trishul, but it has nothing to do with that. E is actually the energy, so that's a variable. Psi is the wave function, as we call it. But H, M, and D are the three most important characters in this equation. So if we understand what they do, we will be able to get a good idea about this. So these three quantities have different dimensions. M is the mass, E is the charge, H has the units of energy times time. We call it action, much like in movies, and this is a talk about dynamics. So this is one fundamental unit of action in nature, right? So we can do a simple game. Can I take these three actors and arrange them somehow, add them, subtract them, multiply them, divide them, do whatever I can, and get some duration of time from this. Right? Can we do this? This is a game that physicists like to play. And if you are a physicist, this is an assignment question for you. Construct a time scale from these three quantities, H, M, and E. How would I do that? Let me think about what I did in the previous problem solving exercise, right? I got a velocity. Everybody knows velocity or speed is distance divided by time. That velocity is c divided by 137. C is the speed of light. And with a little bit of jugglery, you can take my word for it. This is the same as the square of the charge of the electron divided by h. We put a slash on h because that is h divided by 2 pi. You can think of it as a style statement by physics. That is good enough for the moment. It's nothing very different from h itself. This factor 4 pi epsilon naught comes about because we use the matrix and not say the incidence or whatever. So I put it in the brackets. It's not super important. So take velocity and then take how much energy, kinetic energy does the electron have as it circulates around the atom, right? That picture is wrong, but let's still hold on. It's a simple, useful thing. Again, I write down this energy. Look at this carefully. I write it down using m, which is the mass of the electron, e, the charge of the electron, and h, Planck's constant, or the unit of action, right? I got velocity, I got energy. Now, I told you that this number h has units of energy multiplying time. So now I have h, that is Planck's constant, e, the energy, right? So take Planck's constant divided by this quantity c, which makes energy, and that will give us a unit of time. And this unit of time comes out to be 24 times 24 atoms. Of course, this is another numerical exercise that anyone can be asked to do in the first quantum mechanics course. So 24 attoseconds has something to do with the hydrogen atom and the life of the electron in this thing, right? An earlier estimate said 150 attos. Now another estimate says 24 atoms, right? So that is essentially something like the day or an hour or a minute in the life of an electron, which is an electron were to be a character in a science fiction movie, right? So an attosecond is related to the unit of time in the atomic universe, right? So we live 100 years, but electrons live forever, right? So if you think about an electron, in 1 second, it has lived the lifetime of what a human would perceive like to be a universe. So these are immortal, supernatural characters, right? So the best science fiction is also the best, and the fiction also comes from science. That's why there is science fiction. So an attosecond has something to do with the very fundamental unit of time in the universe of electrons, protons, and atoms and molecules, in the world that actually makes us perceptible, the world whose chemistry, whose biology, and everything drives us, right? So therefore, doing physics, taking snapshots, working on these time scales is indeed something which should be very insightful about fundamental processes in nature on these time scales. Now, just as a thought, Professor Govindrajan is an expert in gravitation and cosmology. We did not look at the gravitational constant G. So maybe if you're a physics student, take H, M, E, and G, the gravitational constant, and try to construct a unit of time and think about what that unit of what those scales of time would mean. That would yield us almost another different but very interesting universe, which we are still in some ways struggling to understand, because this H, M, and D is quantum mechanics, G is gravity. So far, even the best minds and all of human effort has not been able to marry these two. So sometimes little games can be very insightful. Now, while all this is true, the picture of the hydrogen atom that we had in computing the time, the lifetime of an electron is very fine, but that's a very boring life, because there is a notion in quantum physics that if the electron is in one of its home grounds, which we call the 1s orbital, then it pretty much lives there forever. Pretty much nothing happens to it. The system is extremely stable, extremely stationary, nothing moves, no dynamics. Because if it did, we would all not be such stable, living entities. We would have collapsed, something would have happened, or whatever. So this notion of things being stationary or stationarity is built into the framework of this theory, because that's what we observe around us. So dynamics does not, unfortunately, happen unless we do something. So in this sense of thinking, how does dynamics happen? We have to create so-called wave packets. What are wave packets? Wave packets are dynamical entities which are created in the following way. And now, once again, lest I sound too abstract, this is the challenge of a talk like this. There's a very young member of the audience from high school, and there is a physics professor in the same. The spectrum is very broad. So let me try and satisfy the curiosity and questions from both. So we have this notion of an eigenstate, a state of motion, a state of being of the system, in which pretty much nothing happens, everything is stationary, stable, fine. It's like live peacefully and happily ever after. Right? So in the hydrogen atom, the probability of finding an electron can be plotted as a distance away from the center, which is the nucleus. There are different ways in which the electrons, different states in which the electron can be found. The first of which is closest to the nucleus, is called the 1s. The neighboring one is called 2s, and then 2p, and so on. These are all, you can say, the houses in which the electrons live, right? In order to create some dynamics, what we essentially need to do is to make a superposition or a combination of two states of these, right? So that superposition is done by adding two eigenstates, and once we do this, or once we somehow create this, we have what is called a wave packet. So a wave packet is essentially a sum, a coherent sum of any two states of an atom. It's not possible for two people to sit on a chair because of the nature of who we are. At the same time, there can be two beams of light which are shining on the same chair. Right? Essentially, owing to the nature of these particles, they can be either superposed or they cannot. So, in the case of electrons in the quantum world, this idea of adding two states or superposing them to be more exact is very fundamental, and that is one signature of the quantum universe. For example, quantum computing and a lot of quantum technology relies and exploits the fact that quantum states can be superposed. So the moment we superpose two states, dynamics begins, and a whole lot of things can happen. But for the physicist, the engineer, the mathematician, the chemist, whoever can follow these equations in this audience, just look at the fact that I've just superposed these two states, what I call U1 and U2. We add these two up, and any observation that we can make on the system essentially can be has to be the absolute value square of this superposed function psi, as we learned in quantum mechanics. We do all this, and in the process, we get a term. We get a term. The only term in this equation which has time is where I've left my pointer. It is in the complex exponent. It is E2 minus E1 times T divided by, once again, h bar comes about, right? E2 and E1 are the energies associated with these two states, right? T is the variable. So what does this tell me? E to the power I, you know, is cosine plus I times sine. So take the trigonometric function, cosine. So this is cosine E2 minus E1 divided by h bar times T. Okay, so whatever multiplies time is essentially frequency in this entity. What this tells me is that this system has some oscillatory behavior with an oscillation period, which is again h Planck's constant divided by energy. This is what we did in a different way earlier. Take the Planck's constant divided by energy, you get that. So I've now done this in a slightly more sophisticated way. This is even more representative of the physics that can happen inside an atom or inside a generic quantum system involving two eigenstates or key states of the system, right? So h divided by delta E is the natural time scale. What does this tell us? Larger the delta E, faster the dynamics or oscillation. Right. So now let us quote this logic and do the entire thing in a somewhat pictorial way. My first state U1 is the 1s state in the hydrogen atom, which I showed you. U2 is the 2p state. Now I superpose these two. I've written down the exact expressions for the wave functions that are associated with the 1s state and the 2p state. But you don't really need all this information. What you need is the energy associated with the state minus 13.6 electron volt is for 1s. It is minus 3.6 electron volts for 2p. These are the only two numbers we need. So please start subtracting these two, right, in your minds. But what are these two states, and why did I say that it's not really correct to say that electrons are going around the nucleus in the form of a planetary orbit? That's because this is really how an electron should look inside the atom. This is like a ball. Okay, this is a probability map of the electron inside the hydrogen atom. When the electron lives in the 1s state, its Facebook profile is spherical. Okay, when the electron lives in the 2p state, its Facebook profile is like a dumbbell. So it appears like two different people. Now, when we superpose them, this sort of dynamics happens. Now please watch the movie that is evolving. We have just superposed them, and there is some kind of dynamics happening, right? So there's a beating between these two states, as physicists would call it. See, from the sphere, sort of dumbbell evolved again. So this is really the way in which the life and motion of electron in this science fiction movie happens. So it keeps flopping and whatever. Now, if I ask myself the question, these oscillations, how much, on what time scale did they take place, right? The time scale I can immediately compute because it is the difference between 13.6 eV minus 3 eV, that is about 10 eV here, and I have written the Planck constant in terms of energy times time units, that is 4 eV times 100. It is 400 attoseconds. So once again, attoseconds. So these attosecond is the natural time scale for electron dynamics in these atomic systems. Okay, very well. We spoke about atto. We learned how to create an attosecond electronic wave packet on a computer. So go back home if you're a physics student, take your favorite program, Python, MATLAB, Mathematica, whatever else, and take down, maybe open your book and put down the equations and start simulating the dynamics. You can very easily do that. You can even take the help of online fora, there's some pieces of code may be available, but check them yourself. So, attosecond dynamics takes place or is important for the life story of an electron. But an attosecond is 10 to the minus 18 seconds, and we spoke about femtoseconds earlier, 10 to the minus 15 seconds. A picosecond is 10 to the minus 12 seconds. So nature is essentially dancing on different time scales using atto, femto, and picosecond, the wave packets and entities. So what do femto and picosecond time scales correspond to? Now we are in a position to get an immediate insight into this because we understood how an attosecond relates to natural phenomena. It is electronic motion. Now, how much heavier is the proton compared to the electron? 1800. Very accurate answer. I think it's more than I remember. I thought it was 2000. Right? So it is 2000 times heavier. So the inertia of the proton is a factor of 1000 higher than that of an electron. So we can expect that the dynamics of protons would be a factor of 1000 slower. Therefore, that dynamics should take place on femtosecond time scales, right? So if I make a molecule of hydrogen, there is two hydrogen atoms, and a molecule of hydrogen essentially can also vibrate. Two nuclear centers, hydrogen 1, hydrogen 2 in the molecule can vibrate. Simplest kind of vibrational motion that we can think of. The characteristic time of this vibration is in femtoseconds. Once again, you can get this picture more exactly by playing the same numbers game. You can take h, Planck's constant. You can take m, now the mass of the proton, and again e, which is the charge the proton would have, and put it do the mathematical generally, you would again arrive at this is a representative number, right? Now, what about picoseconds? This is a bit trickier. If I take a molecule, this is a water molecule, for example, and in our microwave oven, when I put in my coffee, I want to warm it or heat it or boil some water, put it in, and I say, okay, set 130 or 1.5 seconds in it. That's my standard time for heating my coffee, and put the microwave on. It heats food where it is, right? Why does a microwave oven, or how does a microwave oven heat food? It essentially sends light waves, and which are appropriate to make the water molecules inside all our food systems to basically rotate, right? It rotationally excites. So this is electronic excitation, this is vibrational excitation, this is rotational excitation. So microwave ovens are ovens which make water molecules spin like tops inside them. So the heat is energy is absorbed by water molecules, they collide with other molecules around and end up heating the food. So picosecond motion is essentially characteristic of rotational motion. And all this essentially is quantum dynamics. Why? Because as I explained to you, these are all wave packets. All quantum dynamics happens through wave packets. And that is an important lesson that we must take away from the initial slide of the talk, because we are going to apply and talk about this in the remainder of this seminar. Now, the buzzword of today is quantum, right? 10 years ago, maybe even 5 years ago, it would have been nano. So, I would like to convince you through the rest of this talk that attosecond laser pulses or attosecond pulses are a part of a quantum physicist's dream too. Okay, both the ultra small dimension of the universe in terms of space, which is x, y, or z for a physicist, and the very short time durations that we are talking about now. In both these scales of space and time, quantum behavior of matter is natural. It simply pops up. You don't need to do anything much. The phenomenon of quantum mechanics pops up. For example, look at this, the picture of this very famous quantum photon, in which 48 iron atoms are sitting on a ring absorbed onto a copper surface. Okay, this is an iconic image. The spatial analog of a pulse, which is a microscope, essentially took a picture of these 48 iron atoms sitting on the surface, but you see at the center of it there was a blip where there was actually no atom. Okay? So this is because of an interference of the wave functions of the electronic wave functions of these 48 atoms, that in the center you saw something that is totally unexpected. That's the quantum phenomenon. Okay? So on an angstrom time scale, you just need to place atoms and quantum mechanics pops itself out. Likewise, one can expect, and we more or less showed this to ourselves now, that on attosecond time scales, if we observe nature, predominantly quantum behavior will emerge out in the form of the science or nature papers that one can publish. A good indicator of a field burgeoning, becoming mature, and ready to sort of take on a lot of important scientific questions is to look at how much the quantum of research which is done in the field, and this is the way in which the bibliometrics or the number of citations to papers relating to attosecond physics has gone. It has been growing linearly, or perhaps even better, and several articles made it even to the cover of important journals like Nature and Science, which capture contemporary developments in the scientific world. But I'm going to surprise you now with telling you the truth. There are no attosecond lasers on the table. So you must have heard in popular media that this year's Nobel Prize was given for attosecond lasers. This is a bit of a misnomer, of course. For a non-specialist presenting this in a YouTube channel, it may or may not matter too much. But strictly speaking, attosecond pulses don't come out of a laser like the laser pointer which I'm holding in my hand, or even a bigger laser. We need to do something more. Okay. If it was in some sense just the invention of an attosecond laser, perhaps it may not have been as interesting to give away a prize, because there was already a femtosecond laser which got the prize about 5 years ago in 2018. So what is the big deal? You went from femtosecond to attosecond. You already went from nanosecond, 10 to the minus 9 to picosecond, 10 to the minus 12 to femtosecond, 10 to the minus 15. So why should this merit a prize? Right? So the point is that in order to make laser pulses which are a few or few tens or few hundreds of attoseconds long, as one of the prominent leaders in this field says, the inventors of the laser could have foreseen that a femtosecond laser came out of their technology, or a picosecond or a nanosecond. In fact, the first laser to be demonstrated was a nanosecond laser, right? But then, as Paul Qualcomm says, in order for them to realize attosecond pulses, some new physics was essentially required. That's why it took us a lot of time going forward to make this break into the world of attosecond. I must add a little word of caution here. Although I said there are no attosecond lasers, I should strictly say that there are no tabletop attosecond lasers. Now there are accelerators, linear accelerators for free electron lasers, which are starting to produce attosecond pulses more or less directly. This point may become clearer as we go along in this talk. If we look at the history of development of short light pulses, the width of light pulses, and compare that to electronics. In fact, this was a slide I presented 5 years ago in the talk here, and it still remains true that photonics beats beats electronics in terms of clock speed. This blue curve is how faster, or the switching cycle, how much short the switching cycle, that is the flip-flop cycle inside an electronic device like a cell phone, has become over a period of time, all the way from about the 80s to now 30 years down the line. They have made tremendous progress in electronics, right? That's why we have cell phones and so many other things. But on the same scale, if we looked up the numbers for photonics has been much faster. It's just that we cannot make all photonic devices, which is why photonics plays a more circular role in technology. But then there is a cusp here around the year 2000, which is quite visible when attosecond pulses were invented, and in some sense, a new trend has begun in terms of our ability to produce pulses to study science and use them for technology. What and how did we generate attosecond pulses? The genesis of all attosecond pulses begins with optical lasers, right? Lasers of which are no different in terms of philosophy of how they produce light and this laser pointer. In fact, red colored lasers play an important role as mothers of attosecond pulses. So lasers are what we need, are the first step to generating attosecond pulses, right? Now, the Nobel citation, particularly for this remarkable lady, Professor Anne. She's both a very impressive researcher and a great teacher. A story goes, and if you have perused social media around the time the prize was announced, she got the news that she got the Nobel Prize when she was teaching a course on atomic spectra in Film University. So she normally doesn't like to be interrupted during her lecture, but this was a very important call. They gave her the phone, so she took the phone call. They told her that you got the Nobel Prize. So she said thank you, and there was a few minutes of talk, and then she put her phone away and went back and completed her class. And then the celebrations began. She didn't want to truncate her class even for winning the Nobel Prize. So very committed teacher. In fact, I had the honor of attending a workshop in which really taught us about attosecond pulse generation as a PhD student, and also another workshop sometime later on. So Anne is a very special person and scientist, and here, of course, a point must be made, and this is something which she was also asked about the presence of women in science, and especially in physics. So in the physical sciences, there's still a lot of scope for one half of humanity to play a more significant role, and for the ladies who are pursuing science, especially photonic science, she is a role model and an icon, and also for men like us, right? But then she was the one who first observed attosecond pulses. So you can say that in as much as Madame Curie was the first to basically figure out certain aspects of radioactivity, and Julie did the same for photon science in terms of attosecond pulses. It's curious that these attosecond pulses are the soft X-rays, so there is a coincidence. And the citation reads that in 1987, Julie discovered that many different overtones of light arose when she transmitted infrared laser light through a noble gas. And Julie has continued to explore this phenomenon, laying down for some. So, as a postdoctoral researcher, she was working on measuring atomic spectra, which are created by exciting atoms, a flow of atoms, as is shown over here. Excite them with a short, intense laser pulse. In fact, the laser pulse was a red pulse, titanium sapphire pulse of the kind that the pioneers who got the Nobel Prize in 2018 gave us. She focused them on the jet. Out came other colors, and remarkably, the properties of the light that came out were so surprising that she instantly realized that this is not normal fluorescence emission. So, what is fluorescence emission? Take a candle flame, right? Take a substantial chunk of salt, if you can, and hold it with some tweezers and burn it in the candle flame to start seeing colors emerge out. In some sense, this experiment was not philosophically or even methodologically very different. The sample here was noble gas like argon, I think. Instead of the flame of fire, you had a flame of laser focused onto it, and new colors came out. But then, when you expose a bit of salt to candlelight, the light that comes out is a bit like incandescent lamps that are coming out, right? Whereas the light that came out from this turned out to be extremely special. In what way was it special? We will explore that. That's the beauty of science, that nature manifests herself in very unexpected ways, and the scientist must be prepared to receive her. Or, as Louis Pasteur said, fortune favors the prepared mind. So she was a prepared mind, and she saw it. Maybe others. This was such a simple experiment. Anybody with access to these, facilities, reasonable facilities, could have done it. It's not even very extraordinary thing, right? In terms of facility, but she had her eyes, her mind, everything open to perceive what was happening there, and figured that something very interesting was happening. And this was published in this paper in Journal of Physics B, which has 2,000 citations. Okay, for those of us who are publishing work, this is not Nature Science or a very fancy journal, but then you see pioneering work gets published in many of these benchmark journals. So if you're a PhD student and you, like every researcher, you have to face some journalistic rejections. Don't get rejected. Publish it, and the world will take notice of you. This is a lesson I learned from these experiences, and perhaps young folks here can also keep that in mind. So this paper now has several continuing growing number of citations. So then a laser was really important for serendipitously discovering attosecond particles. Let's make a small detour over here and look at what is a laser. Almost everyone here has used a laser, but then if I were to build a simple model for a laser which is fairly accurate, the laser consists of two mirrors, the green and the yellow squares over here represents two mirrors. We call them N mirrors. The purple thing inside is called gain medium. The green is a source of energy that pumps this medium to get gain out of it. The laser is essentially an oscillator, a resonator, in which light waves are confined and contained. Okay. The laser is a light container, just like this glass, the water container. Okay. In fact, there are some further similarities. This also has a very nice smooth shape, like an optical resonator should have. So light waves stand inside laser cavities. This is true also for acoustic instruments, like a drum, like a violin, like a tabla. Next time we look at them, all of these characteristically contain an object which contains sound, in which sound waves stand, and a part of the waves that are standing inside start emanating out. So the holes in a violin, for example, remember that they essentially take a piece of the acoustic energy which is present inside the cavity and bring it out. So this is true for acoustic instruments too. A laser does something very similar in the optical domain. So a typical laser is this resonator plus a gain medium, which essentially enables coupling energy from another source into light energy. Now, the laser that Anlulia used and people use today to generate attosecond pulses it's a pulse laser. So, what is a generic pulse laser? In a typical pulse laser, you not only have the two mirrors, the green and the yellow, the gain medium, the purple, the pump. You insert inside this a pulse shortening device. Okay? It is not anything very remarkable. So it turns out that you put a modulator inside, and the same laser which was operating as a continuous stream, as something which produced a continuous stream of light, now starts to produce light pulses like this. It starts to produce flashes of light. So all you need is to insert a pulse shortening device, which could be an acousto-optic or electro-optic modulator. So the key thing is the modulator. The necessary condition for producing pulses successfully from such a laser is to ensure that the frequency of modulation that the pulse shortening device acts with essentially should be equal to the frequency with which light circulates inside this cavity. Because there are two mirrors and light keeps bouncing back and forth, light circulates in this cavity for a certain time period, and the frequency, the modulation frequency, and what we call the cavity, the resonant frequency of the cavity should match, then we start getting flashes of light. So generate pulse laser is a generic laser plus a pulse shortening device. So this is another view of what is happening in a pulse laser. Pulses keep circulating back and forth with the laser, and essentially at one of the mirrors partially lets a bit of these pulses come out, and that's how we get light pulses out. There comes out a pulse and so on. So these lasers emit a periodic train of pulses, blip, 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 as a function of time, right? So these pulses, if we do our job well, can be of femtoseconds in duration. Why do we get femtosecond pulses? A little insight into this, especially if you are a student of physics. The resonator or the cavity that the laser is made up of can sustain waves of slightly different frequencies. The pink one, the dark pink one, and the blue one, they have slightly different frequencies, so number of cycles per second. And if these waves are locked in their places, then what we see is an interference pattern like what we must have studied in optics in the spatial domain, like grating. So if this sort of locking of the phases of the different constituting frequencies of the resonator is done, then we are set to achieve mode locking. Because the different modes, you lock the modes and the frequency, don't allow them to essentially move around freely, somewhat like there's a frequency of chairs in this hall, and we are occupying these chairs, and we are kind of locked in our position in space. So similarly, these modes are locked in their position in terms of time, and interference between these happens, and it's almost pictorially obvious that light pulses, which are periodic, emanate from this. So that is a typical mode lock wave. Now, at visible wavelengths, one time period of any of these electromagnetic waves of any of these modes is a few femtoseconds, 3 to whatever femtoseconds. Therefore, when you form these interferences time with the waves of the optical domain, these turn out inherently to be femtosecond pulses. The duration, the on, here the pulse is off, it is on, it is off, it is on, it is off. The duration for which the pulse is on is essentially of the order of femtoseconds. So locking the modes of the laser is all we need to do to get femtosecond pulses out, right? A closer look at this. Now I have plotted 6 cavity modes over here, and at what I have called 0 of time, the horizontal axis is time, vertical axis is some kind of amplitude. At 0, all these waveforms act constructively, and out comes the pulse. As I go away from 0, the maximum of one piece of the maximum of the red wave and the minimum of some other wave, the blue, tend to cancel out each other. So at all other instances outside the pulse, the waves are interfering destructively and are working against each other, and therefore the amplitude of the electric field turns out to be 0. So this is the microscopic detail of how mode locking synthesizes femtosecond laser pulses for you. Now, this is a matter of maybe detail, but a nice insight. If I let a pulse propagate in space, let's say it originates from my end and moves towards the other end of the hall, then all that happens is that these waves have started to move around, and now the point at which they constructively interfere has moved forward once again, and all their heads meet up in time at a point that is further away from me. And this process keeps happening. So this is how, in a sense, light propagates. Phases are the most important entity. Now, in order for attosecond technology to be realized, it is extremely important that we have sufficiently energetic femtosecond pulses. And who ensured this? The laureates, about 5 years ago, were given a prize for their method of generating high-intensity, ultra-short or femtosecond optical pulses. Gerard Moreau and Donna Strickland. It's a pair of PhD advisor and student who got this prize. Again, quite remarkable that they invented this technique, which is the genesis of attosecond pulses. And in fact, just to show my memory, in June 2019, I had the pleasure of presenting the underlying story of these fascinating tools, like beams, very much in this hall, and the deja vu is a very pleasant one. So, but then let's go back to Lulier's harmonics and ask what is behind them and what are the very interesting features that they observe. So these are the harmonics. What is a harmonic? I have frequency, say omega. A harmonic, the second harmonic of the frequency omega is omega. The third harmonic is 3 omega. Fourth harmonic is 4 omega. It so happens that in the process of generating attosecond pulses, what we are doing is essentially generating harmonics of the primary light wave which created this beam. So on the scale of wavelengths, note here that the scale is 60 to 100 nanometers. The harmonics all the way from 9, 11, 13, 15, 17, 19, 21 are appearing in the spectrum. So this is the spectrograph of what she saw. And she did a very careful measurement. She took harmonics of different order and plotted the relative intensities of these harmonics. Okay, after correcting it for instrument biases and so on, she saw that initially the first two harmonics, the relative intensity with respect to each other drop. This very sharp drop, but then there is a plateau which occurs over here, and then there is a cutoff where beyond which harmonics are not produced. So the harmonic spectrum or the high harmonic spectrum essentially has a very prominent plateau region and a cutoff region. These are two signature aspects of a high harmonic spectrum, or what we call attosecond pulse generation. This was really curious because the physics of the time did not quite know how to interpret. So one can take a step back, and this is something we discussed 5 years ago in the context of the earlier Nobel Prize, that ordinary harmonic generation, you take omega, you go to 2 omega, you go to 3 omega. All this is well understood in this picture, where the polarization of matter is either dependent on E, the electric field, the square of the electric field, or the cube of the electric field. So since it's quadratically dependent, second harmonic comes out. Since there's a cubic dependence, third harmonic comes out, and so on. So this physics is fairly well understood. It's also taught in our master's courses in many places, right? So the math of this also can be easily written down. Write down the electric field as E, the amplitude times exponent of I omega t, square it, and immediately comes the second harmonic term. But then the interesting aspect is that this type of nonlinear optics did not explain why there should be a plateau in the high harmonics that was observed by Lullier. Look at the numbers here: 7th harmonic, 11th, 15th, 19th, 21st, and so on. Why is there a plateau? This was the question that really bothered all physicists of the time, right? So it took a while for people to figure out, and once again, Professor Einstein comes and says, think about what you must be doing wrong, or think harder. You'll get an answer to this, the mystery of the plateau of high harmonics, right? So this indeed turns out that we need to think really beyond the perturbative picture of optics and understand the fact that at the intensities at which these high harmonics that were observed by Lullier were produced by a laser, at these intensities, the process that is happening is something very different. It is something which Oppenheimer foresaw in 1938, right? So at these intensities, considering direct photons of energy of about 1.5 eV, they can pretty much not ionize any atom, but we go back to the hydrogen atom and subject it to the kind of electric fields that were done in the experiment. If we do that, then the potential which we looked at earlier has two terms. One is the 1 over r term, which is shaded in gray. The other is the second term, which also is pretty strong in this case. It is E times R. It is what we call the perturbative term. This is the electric field of the laser multiplied by the distance away from the nucleus, which the electron is the coordinate for the electron. essentially in the nonlinear optics, where second and third harmonics are generated, the violet term is pretty weak. It does pretty much nothing to the very strong term about the native fields in the atom. Whereas in this case, the violet term turns out to be pretty strong and starts to challenge the native fields inside the atom. When this happens, essentially the following happens. So the electron lives in the 1 over r well, right? So the 1 over r well is like my arms. The electron is like my head, right? So what happens when the light field comes? It starts to bend the potential which holds the electron. Okay, it starts to bend it. This is the effect of the E dot R term. Okay, now if it can so happen, my head can roll off on the right side. So nothing is holding it there. That's exactly what happens to the electron. Now, when the electric field reverses direction, this potential side goes up and the other one goes down. So in an electric field, this is what is happening inside the atom. The potential keeps flopping with time and keeps getting deformed continuously. And so the electron essentially comes out of the atom and does things in order to produce these harmonics, right? So I'm not going to go into the details, but in order to explain the spectra of harmonics, two characteristic energies are very important. One is the ionization energy of the atom, that is of the electron in the atom. This is the energy required to remove the electron from the bound atom and put it out in the space somewhere. That is called the ionization potential or ionization energy. This is well aware of. There is another characteristic energy which is called the quantum motive energy. This is the average kinetic energy that the electron obtains from the laser field once it was driven out and performed its dynamics. So the average kinetic energy of the electron in the laser field is linearly proportional to the intensity of the laser light, as we should expect, but also quadratically depends on the wavelength. This is a matter of physics details, which we went up. Now, somebody came up and, understanding this particular insight, explained the entire mystery of the plateau and cutoff of the high harmonics that Annulier essentially saw. And a simple model was presented by Professor Paul Corcoran, in which he said that in the first step, the electron is essentially, which is bound to the atom, escapes. In the second step, it tunnels out through the barrier that was deformed by the electric field of the laser. And in the third step, this electron, which was moving away from its parent nucleus, came back and recombined with it, and harmonics were emitted. This is a very simple, intuitive picture of what could be happening underlying the harmonic generation process, the famous three-step model. First step, the laser field is short and the electron does not have enough energy to lift itself out of the well. In the second step, the electron tunnels out and starts moving away from the parent atom. In the third step, it reverses its direction and recombines with the atom. It turns out that when the electron recombines, photons are emitted, electromagnetic waves are emitted, and this is how high harmonic generation process takes place. So this is the fundamental piece or the missing crucial piece of physics, which there was no way to foresee this and to predict the occurrence of attosecond laser pulses right when maybe optical lasers were made. This is the new piece of physics that was missing, and somebody came and explained it. Professor Paul Corcoran, very impressive physicist who has all the prizes except the Nobel Prize. So there is, of course, a chatter in the community about why he was not one of the three. But that's the feature of the Nobel Prize. It is a recognition of the entire field of study, an entire branch of physics, and unfortunately, according to Alfred Nobel's will, only 3 people can be recognized by the prize. So for the 3 that were recognized, there are probably many important contributors who were not given the prize, but are essentially fathers of the field, and Professor Corcoran is one of them. He wrote a paper which he solely authored in this very nice journal, which is today cited almost 9,000 times, right? So very impressive, iconic figure in this area. Now, why was this model or how was this model successful in explaining the features of high harmonics? That's the elegance and beauty of this three-step model which is being called, or the simple maths model, that you only need to solve Newton's equations and you get some very important insights out. The cutoff region for high harmonics obeys this equation. This was something determined in experiments. IP, the ionization energy, plus a factor of 3.1 times, 17 times, almost 5 times UP. UP is the quantum motive energy, average energy. I told you that this is essentially I times lambda square multiplied by other factors. So you can set this by tweaking the intensity of the laser in your experiment or changing the wavelength of the laser. The cutoff frequency for high harmonics is IP plus 3.17 If I can get this right based on the three-step model of Corcoran, then the model must be largely correct, right? So Corcoran wrote down the Newton equation, acceleration equal to force divided by mass, right? 1 over m, mass of the electron. E cos omega naught t is the instantaneous field of the driving laser. So integrate this out, you have velocity is equal to E naught by m omega naught sine omega t plus an initial velocity that one should know. Integrate this once again, you get minus E naught square by m omega naught square cos omega t plus a linear term in time vi of t plus an x side. So what does all this mean for us? All this tells us that essentially the energy of the electron that is traversing in the space and coming back and recolliding, in a sense, depends upon these initial conditions, the initial xi and the initial vi, right? But then we are talking about dynamics, so I can translate these initial conditions in terms of time and ask myself the question: at what time, okay, during the laser pulse's interaction with atom, be the electron born so that it gets maximum kinetic energy, acquires maximum kinetic energy. At what time should the electron be born? Okay. So we can do the math over here. At what time should it be born? Vi depends on that, and therefore do a bit of differentiation. And it so turns out that if omega naught is the frequency of the light beam, and T naught is the time of birth of the electron, if the electron is born at a phase that is omega naught T naught times T naught of 17 degrees, or identically 180 plus 17, 197 degrees, at these two special instants of time, okay, this is measured with respect to the maximum of the electric field, okay, then the electron can have the maximum, can benefit maximum from the driving laser field's energy. Okay, so the kinetic energy for this phase turns out to be 3.17 times the maximum kinetic energy turns out to be 3.17 times the average energy. And when such an electron returns to its mother ion and recombines, it has the photon that comes out has two components of energy. One is the maximal energy that the electron had, which is 3.1% Q plus IP, the ionization energy. Right? So that is as far as the photon energy can go, and therefore cutoff of the harmonic spectrum is IP times 3.17 times UP, the average kinetic energy. So this simple model explains the cutoff energy of the harmonics, and therefore this turns out to be the insight that we need to understand Professor Lully's harmonics, right? So first, tunneling, acceleration in free space, recombination. These are the three steps of the three-step model. Now, why do we get attosecond pulses out of this, right? The primary laser that was driving the field over here is the red laser cycle. The attosecond pulse emission, or the emission of these harmonics, is concentrated to those regions where the electric field is very strong or maximum, which is the peaks of these electric fields, and all the action of generating harmonics essentially is centered to these, right? Since each optical cycle here is about 3 femtoseconds, only a fraction of the optical cycle contributes to the generation of these harmonics. And therefore, these harmonics come out as bursts of pulses, and these bursts are attosecond pulses. In the case of any laser that is used for high harmonic generation, a piece of an attosecond pulse is generated at every half second, either this positive maximum or the negative maximum. So we get 2 attosecond pulse bursts for every 1 optical cycle, as it is shown over here, and attosecond pulses are therefore separated by twice the frequency of the mother laser that is driving it. Okay, so this immediately tells us as to why we see the harmonics to be 3, 5, 7, 9, so on and so forth. There are other technical reasons as well, but typically lasers produce trains of attosecond pulses and not necessarily single attosecond pulses. This is the time domain picture on the right panel, and the left panel is the spectrum of attosecond pulses. Right. We also know that light pulses have this inverse Fourier relationship. If the pulse is long, the spectrum is narrow. If the pulse is short, the spectrum is quite broad. So attosecond pulses also typically tend to have substantially broad spectrum, which in a way comes for free from the way in which these pulses are generated. This is a view graph of an experiment in which this is done. So these are the atoms, these are the orbitals of the electrons shown over here. The electron leaves the parent atom, it comes back, recombines, and at every half cycle, an attosecond pulse is generated. So the radiation that is generated like this is shone onto a grating. Many of you may have done experiments in your undergrad lab or even high school using grating and white light to generate spectra. The grating then separates the wavelengths, and on the detector of a spectrograph, you see the spectrum, the high harmonic spectrum that constitutes the attosecond pulse. Okay, now matter of detail, I will not belabor this too much. Just as in all cases, we have a classical mechanical picture. The same 3-step model was later written down formally by Rubinstein and others in terms of quantum mechanical model, in which the quantity of interest that we want to determine is the time-dependent dipole moment of the electron atom system, electron nucleus system, right? We take only one active electron at a time and write down its dipole moment. It is quite complex, not a straightforward expression right now. However, the 3 steps of the model were incorporated into a quantum mechanics network by Max Planck, in which this term corresponds to the ionization term, where P is the momentum of the electron, K is the vector potential. Then the propagation phase essentially is e to the power is, where s is the corresponding action. And the third, this piece of the puzzle is of the equation is recombination, right? So in this case, a wave packet which was bound in the nucleus around the nucleus propagated out, came back, and a part of it recombined. This essentially is the insight which we got. In fact, there is a second iconic paper by Kullander, Schaefer, and Krausz, which essentially is a different Krausz, not Ferenc Krausz, which was published around the same time as that of Paul Corkum in actually, I think, in a conference, which brought up this quantum mechanical picture that is captured in the Rubinstein figure. So this field, in fact, has benefited from the remarkable effects of several physicists, right? One technical point, if you're an aficionado of optics and nonlinear optics, it's not one atom that generates an entire harmonic spectrum. It's a whole group of atoms which do that. The beams that are observed, the attosecond light pulses and the beams of attosecond pulses observed, essentially are a signal that is coming out of, say, 10 to 10, 12 atoms which are present in the focus of the laser. The radiation will be observable only if the emission from all these is coherent, they are all in step. So this needs to be ensured by the experimentalists who doing this measurement, and we need to ensure that there is sufficient coherence of phase matching between these atomic entities. So physicists take advantage of 2 dispersions that of the neutral atom, and the plasma that is generated, that is involved in the attosecond pulse production process, and they use this, the Bowie phase of the beam, in order to achieve phase matching. So here is a phasor diagram that is representative of how a phase match scenario versus a non-phase match scenario would add up in produced pulses or not produced visible pulses. Once again, this is a matter of technical detail, but if you are interested in these details, this is something which you probably should know. So the generation of attosecond pulse trains involves essentially the three steps of tunneling, acceleration, and reconfirmation. Okay. Now, in maybe I will take about 15 minutes, 10 minutes.
5:30.
Okay.
Yeah, before this.
Sure. So then I will more or less close with one example of how we apply attosecond pulses to do some physics and technology. How are these pulses measured? Let us maybe discuss that and stop with it. This is the measurement of these pulses was the aspect for which two of the people here got Nobel Prizes, Pierre Agostini and Ferenc Krausz. In order to measure the seconds hand of a clock, we need minute hand, we need a second hand. If there's a seconds hand ticking in the clock, there must be something happening. Millisecond time scale. The technique for how to do this was what gave the Nobel Prize to Agostini and Krausz. But I want to just jog your memory back and have you think about Michelson's experiment in which he determined that there was no ether. It so turns out that I figured that this was the first attosecond metrology experiment done by human beings. The fringe which Michelson expected for the configurations, what he called parallel and perpendicular, it's not important to describe this experiment, but if you're curious, you can find enough nice videos on YouTube to pick this up. Essentially, in this interferometer, he tried to measure time differences between two arms of the interferometer, where the velocity of the light, the size of the interferometer, and the speed of light played a part, and the time difference that they were trying to capture in this experiment was about 80 attoseconds for some nominal numbers, right? So, but this was in the first attempt at Michelson's experiment was done in 1880. He succeeded doing the measurement, I think, in early 1900s, right? Or the reported experiment began in the early 1900s. Almost 100 years ago, somebody had set the platform for doing attosecond metrology with or without realizing that attosecond pulses would be born, right? So, an attosecond interferometer typically looks like this. It's an experimental setup. But then, how do we measure these pulses, which are essentially the shortest light pulses produced by man? If I need to measure a short event, I need a shorter event with that, right? If I claim to have produced the shortest event, how do I measure this? So all the techniques that are used to measure attosecond pulses must be self-referenced. That is the whole idea. We take advantage of the fact that an attosecond pulse train contains several harmonics in the spectrum of the attosecond pulse. And the technique that got two of these colleagues the Nobel Prize is called rabbit, reconstruction of attosecond beating by interference of two photon transitions. So the idea of this is as follows. The harmonic spectrum essentially is harmonic, say 9, this is 7, and this is 11. Now you shine this light on a piece of gas and remove electrons from argon or typical red gas atom like that. Because of the frequency content of the light, which is shown on this atom, electrons come out with kinetic energies which are corresponding to the smallest harmonic, the middle harmonic, or the farthest harmonic. So, say there are 3 peaks in the photoelectron spectrum. Along with the high harmonic spectrum, the mother laser is also interacting with the same set of atoms. Now, what happens is that a mixing between the harmonic spectra in the black and the mother laser happens, and satellite spectral lines are seen in the photoelectron spectrum. Here or here, right? So these side bands can be formed either by adding one red photon to the lower harmonic or subtracting one red photon to the high harmonic. The sideband can essentially be formed by two routes. So this is like an interference, and this is a typical experimental result of a rabbit experiment in which the sidebands are formed. Now the mother laser and the plane of high harmonics is delayed by a little bit, and oscillations, dark, bright, fringes in time are seen, and it is from an analysis of these fringes that one can determine what the duration of the attosecond pulsar is. This is one more manifestation of this quantum interferometry. Indeed, it covers the experiment in the quantum domain. This rapid spectrum was generated by a student whom I co-guided at the Max Planck Institute in Physics, in Kumar Srinivas. So this is straight out of the thesis, which should also be available online. So if you're very curious about how exactly to extract the pulse duration from the sidebands, that's a very good reference for this. And a complete characterization of the attosecond pulse generated is possible using the rapid technique. And that's why somebody got the Nobel Prize. Now, I wish to tell you one little thing before we close. Well, this is fine, but what can attosecond pulses do for us? There is a very nice technique called streaking, which is enabled by attosecond pulses in the following way. A streak camera is a camera which takes pictures of time phenomena. Normal cameras take picture of spatial objects like the audience here or the person speaking and so on. In a streak camera, a light pulse goes through a photocathode, and the photocathode releases photoelectrons, which essentially mimic the form of the light pulse. But this light pulse is of a very short duration, say a few picoseconds. There are no oscilloscopes which can observe picosecond light pulses. So the way to record an imprint of these light pulses is to convert these light pulses into electron pulses, then make them go through a capacitor where a voltage is quickly ramped up. A voltage ramp is applied on the capacitor, and these photoelectrons, which were traveling in time towards you like this, turn around because a capacitor field is applied, and then this is imprinted on the detector. Okay? So the electron pulse was going like that. Field is applied, it turns around faithfully, and it is imprinted on the detector. From the map of the electrons, from this picture, the time duration of this pulse or the time structure of the picosecond pulse can be generated. Right? So this was a very good piece of technology. It's still being used for characterizing and learning about picosecond pulses. Now, attosecond pulses enable the same for much faster petahertz oscillations that light fields go through. I will not go through a whole lot of the physics of this process, but then what happens is the following. The red laser field is the mother laser field. Okay. At different instances within the mother laser field, an attosecond pulse comes and removes an electron at T1, T2, T3, T4 at different times. Okay. Because these pulses can ionize and remove electrons from the atom, much like in the case of the streak camera. The momentum that the electron has while coming out of this scenario has two components. One component is the mechanical momentum of the electron. The second component is the field momentum. Field momentum is essentially the charge times the vector potential of the field. Which field? It is this red field, okay, of the driving laser or the laser whose field we are interested in mapping. So now, if these momentum changes are measurable, are these momentum changes measurable? Yes, I can measure the change in these momenta using a conventional photoelectron spectrometer. What are these times? These times are a sort of relative delay between the red cycle and the attosecond pulse. This can be set by the experimenter. It's just about using a nanopositioner to do this, right? And I can measure the photoelectron spectrum and do the following. I scan this attosecond pulse over the temporal variations of this petahertz pulse, which is light frequency that we are all bathing in right now, 10 to the 14 hertz or so, optical pulse, right? So as this attosecond pulse scans this petahertz optical pulse, the photoelectron spectrum shifts. Delayed spectrum. Record this like frames in a movie. You literally record this like frames in a movie, and out comes the first ever direct image of an oscillating light wave that human beings have seen. We saw this only in 2004. If you were to ask the next question, how do you know that an electromagnetic wave is an electromagnetic wave with oscillating electric fields? Here is the first photographic answer to that. Right? You could literally see an electromagnetic wave with using attosecond light pulses. So this is the directly measured field. So now think about it. As a student of engineering physics or sciences, we all use oscilloscopes. This is an oscilloscope with a bandwidth of petahertz. This is not available in the market yet. For the first time, we have such a magnificent oscilloscope. What can I do with this sort of an oscilloscope? I will skip this and we will apply this to one scenario which essentially was the reason which Einstein got Nobel Prize for. Right? So Einstein got the Nobel Prize for discovering the photoelectric effect. Now, in the photoelectric effect, what did we learn in our physics class? If you come in with light which exceeds the work function of the metal, then it knocks off an electron, and the electron has a kinetic energy, which is the electromagnetic energy, that is h nu minus the work function of the wave, right? H nu minus work function is the electron kinetic energy. This is an experiment also done sometimes in colleges, right? But now atoms have many electrons. They can have more than one. Everything except hydrogen has more than one electron, right? So now if I come in with a light, okay, and I take neon atoms, it's an experimentalist convenience that made him to take neon atoms, which is a relatively simple atomic system, and come in with photons whose energy is greater than two electrons, which are than the ionization energy of two electrons in neon, the 2p electron and the 2s electron of neon. Suppose there is a photon which can knock off both 2s and 2p, or either one of 2s and 2p electrons. Let's say a photon of energy of about 100 electron volts. Can remove the 2s electron, remove the 2p electron of neon. Now, I can ask this question. It's the same pulse, photon pulse, which is going to remove either the 2s or 2p electrons. Which of the electrons comes out first, and which of the electrons comes out later from that? Comes out meaning, is there any delay between the ionization of the 2s and the 2p electron? This is a question for which, until about 2000 something, we had no direct answer. In fact, photoionization is thought of to be an instantaneous process. Here is a remarkable experiment done on neon atoms and similarly done on magnesium, solid magnesium, along with a cut at the 0, plane. And if I zoom in over here, what people did was a very clever thing. They measured the time profile using a petahertz oscilloscope for the same field, but did that using the 2s and 2p electrons, the red and p. And these two curves are shifted by a very tiny amount. These two curves are shifted by a very tiny amount, the red and the blue value. This shift is essentially coming out because one of the electrons woke up a little later in the turtle, like the turtle and it started its race a little later and came out of that. But of course, I've cartoonized the physics of it. This is called the Wigner delay that occurs in the scattering problem, which was foreseen by Eugene Wigner long ago, and we are for the first time measuring this. And indeed, when we do science like this, something, I mean, it shows power and potential of these techniques, right? So this technique has been advanced. Just as we have spectroscopy, now we can do measurements of physical systems directly in time. It opens up a new field called chronoscopy. This is a study in which tungsten and iodine atoms were also subject to the timing experiment. The absolute timing of the photoelectric effect was done. And today, modern 2023 photoelectric effect is so different from the photoelectric effect physics that was realized in the early 1900s by Einstein. So much so that I believe if Einstein were to be around today, he would have really applauded the facilities and opportunities that attosecond science presented. So that is the generational measurement, and in this case now the application of attosecond physics for you. With that, I thank you for your patient listening. I know I've exceeded the time considerably, but I hope it was worth the while. And if there are any questions for however long we can stay, I'll be happy to take them.
Start with your question. Can attosecond process be created with IIT Madras?
So we are making an effort to generate attosecond pulses in our lab, pending some technical and funding requirements, which are always there, but that is not rigorous. So we will make an effort to generate high harmonics here. But of course, there are a couple of labs in India where this is being done. One in RRCAT in Indore, and there is another lab in IIT, which is also taking off in this direction.
They have already done, or
they have measured some attosecond pulses. I'm not sure that they have published these or other done new research, publishable research yet. But I must be careful in saying that because quite a while ago, RRCAT folks have published high harmonic spectra. So in that sense, yes, attosecond pulses were generated. But to take this forward in the form of attosecond physics and attosecond science as a regular stream of work, that is still something we can wish more for.
So the next time scale will be nuclear.
So Attosecond
24 seconds.
Yes, 10 to the minus 21 seconds, Attos 10 to the minus 18, and Zettos 10 to the minus 21. 10 to the minus 24 is Yocto. But just to break the news, we don't have controlled Attosecond pulses yet. However, there are a couple of papers already where Attosecond timescale phenomena have been measured in experiments. And to give you a very quick postage stamp view of what was done, I was talking all about single atoms in the context of this. Basically, there was an experiment done in which, again, a hydrogen molecule was photoionized. It has two hydrogen atoms. Now, normally, if I remove an electron from a hydrogen molecule, I cannot really localize it to atom 1 or atom 2. They are actually indistinguishable, right? So, but then the experimenters did some very careful measurements of the photoelectrons coming out of the hydrogen molecule and found effects of the fact that the photon essentially ionizes the atom to the left or the right, and if the light electromagnetic wave ionizing this is traveling over the atom, there's a small time difference between an event happening on this hydrogen versus this hydrogen. So for the electromagnetic wave with respect to the source, one of the atoms is nearer versus one of them being farther. So they discern this extremely tiny effect because think about how much time a light wave takes in passing a molecule whose size is maybe 2 or 3 angstrom, right? That distance divided by the speed of light is some zeptoseconds, and effect of this zeptosecond difference was found in experiments. So zeptosecond science is also taking off, although zeptosecond pulses will need maybe further new physics to be learned and used.
Is there any practical application of attosecond pulse apart from studying the atomic world?
So at the moment, we cannot possibly use it. Okay, I should not say that we cannot use. Yes, the time domain application may or may not be obvious, but attosecond pulses essentially are generated in the extreme ultraviolet soft X-ray. So the wavelength of light that comes out is tens of nanometers, or could even be shorter. Now, while they are nice pulses, they are also a source of UV radiation. So now the first application of attosecond pulses, or one should say high harmonics, is being done in metrology industry, where semiconductor wafers and electronics, when they are being fabricated, people have to look for defects, and by the time we get a cell phone of the type that we have in our hand, a lot of processing has happened. So semiconductor metrology companies are always hungry for better and better and better microscopy to be done. We know that the smallest feature size a microscope defect can detect or measure is proportional to the wavelength of the light. Here is a light source on the same laser tabletop whose wavelength is a fraction of optical light. As a consequence, if I do microscopy using this kind of laser, it would help semiconductor metrology a lot more. Therefore, companies like Krausz, who basically make semiconductor fabrication tools, are now beginning to use these type of light sources for doing semiconductor metrology. In one sense, the next frontier in chip manufacturing is 13.5 nanometers, which is also radiation in this domain. Although the process is not high harmonic generation, laser-driven tabletop EUV sources are what will be used in the next generation of lithography. So in that part of the world, high harmonics, which are generated from lasers, are going to start making an impact. But then, on a slightly different note, people are doing this. Basically, there is graphene and there are two contacts on either side. In a typical field effect transistor, you have a semiconducting material and you have a gate, right? You apply potential on the gate and or field on the gate, and field effect transistor happens. So this is a realization of a light field driven, or LFET, light field effect transistor, where the gate is already there and the actuation is done by an electromagnetic wave, and in one sense the plot here corresponds to field oscillation. So in beyond foreseeable future, there could be a time when petahertz becomes the clock speed of our electronics. If that happens, it is due to the developments that people are doing, inspired or in the direction of patterns. So this is technology for the present and some much for the much further future.
Like whether the tunneling thing you mentioned about this, all sense it is only because of the Eva family. Whenever we talk about tunneling, we regard it as because of the contribution from Eva family.
Not all tunneling is due to that. So, good question. The tunneling here that we are talking about, bigger. So here the dotted line, the dotted gray line that you see, is essentially the potential in which the electron is bound by the hydrogen atom without any electricity. The classic 1 over r, which is minus z is just 1 here, minus z by r. That's the potential. Now, if this is to be the case, the electron can never tunnel out because there is no opportunity to. This barrier extension is all the way to infinity. There is no possibility for tunneling. Because of the E dot R term, the potential deforms to the violet shape. So you can approximate this to a sort of triangular potential. Now, because the barrier is deformed, the electron has the opportunity to tunnel out. Right? So because of that, tunneling happens.
There is no maximum for that.
There is no maximum for the other. In other words, a particle in a box, there is no tunneling. If you take a quantum mechanical problem in which the barriers of a particle in the box are infinite, there is no tunneling. You deform one of the barriers, make it finite, then tunneling can happen, right? So in that sense, yeah, I mean the barrier in fact should also go back to zero, then tunneling can happen. So the laser deforms it so that tunneling can happen. So in other words, it's not essential for the E naught R to be present always in tunneling problems. It depends on the shape of the potential. Here the shape is anything from E naught R. Yeah.
Thank you, Professor. Lecture is really informative and to follow. So I have two questions. One is, in popular, after the Nobel Prize is announced, the popular level magazines, popular level website, they think that this discovery, or maybe this Attosecond Nobel Prize development is really breaking the Heisenberg concept. So is it really actually, I don't think, but is it really, can you throw more light on this claim? And the other one is, how is this particular Nobel Prize, this Attosecond development, is able to help the medical field?
Right. So I will answer the second question first. So this any source of X-rays is something which possibly medicine can use for, can make use of. Okay. First of all, one of the first things that what comes to mind when you ask about applications to medicine, or I would take the liberty of extending it to biology, is the fact that if you have short wavelength radiation, microscopy becomes much better, as I was saying. So one can possibly do microscopy with extreme ultraviolet radiation and get the structure of cells and other such biological objects. So in that sense, it could be an alternate platform for microscopy. There are other laser-based methods for generating very fast ions or very short X-ray radiation, which could even be used for therapy, but that is still technology at the time. So that is very likely medical application. This is not to say that there are machines in the market which can do it. We are not yet there. Now regarding uncertainty principle, well, the uncertainty principle essentially says that in terms of position, it is delta x, delta p, right? So should be bound by should always be bound by the Planck's constant, right? In this case, I suppose people are sometimes mistaking the fact that I can take pictures of electron motion. So the picture that we take of electron motion is not really in a classical sense, which is to say that if I were to be able to take a picture of the electronics state every 10 attoseconds or every 50 attoseconds, then I would have taken a picture of frozen electron motion, once again taken another picture of frozen electron motion and so on. I could have computed its velocity from the repetition frequency with which pictures are taken. At the same time, I would also know the position of the electron. But as we really saw in the early part of the talk, what we are doing is not really freezing the motion of an electron and taking a picture or something like that. We are essentially doing time-resolved spectroscopy. We are getting information about the various states of the electron which are participating in the dynamics and the relative phases between them, right? So I would liken this a bit to if you take a musical instrument like a guitar or a piano, right? So basically, we strum multiple strings together and it produces sound. And there is a sequence to this, there is a motion to this music, which is what we listen to and appreciate. In this case, in time-resolved spectroscopy, we are essentially doing the same. However, if I freeze the string and take instantaneous pictures of it, maybe I'll be able to get good photographs, but that's not the case. If I take images of stationary string or if I stop it from moving. So this is a bit like that. We are getting intimate information about the dynamical process. At the same time, what we are not doing is we are not freezing things, taking pictures one after the other and going forward. It simply doesn't work that way, which is actually the uncertainty principle. So there is no violation of the uncertainty principle. In fact, if anything, there is a better appreciation of the uncertainty principle because this entirely wave packet analysis. So that would be my take on this notion of why going beyond the validating concept.
Thank you, Mr. Sivarama Krishnan for participating in the PSL 65. So he did this in 2018. Again, he did the same thing. So it's an excellent lecture. We enjoyed it. Thank you, very much, sir. I would like to thank IIT authorities. They provided the lecture for all apart from the infrastructure, the internet, everything. So thank you very much for the IIT. I'd like to thank Professor Pierre for continuously supporting us for doing this kind of business. Thank you very much. And I would like to thank you. So came all the way from your place and sitting here for 2 hours and listening all this. Thank you very much. Thank you all.
Round of applause for the organizers of the event.
We have 3 oil part of this. I have 2 announcements. One is please provide your feedback. So we got a QR code. Just scan